Panayotis and Mertikopoulos.
All right. Hi, everyone. And Rida, thanks again for giving us the opportunity to do this. Is there also a clicky thing? Yeah, thank you. All right. So, Rida also drafted me in this difficult exercise on why do a PhD, in my case, on learning in games. So, let's start by playing one. And if you have seen this, don't speak up. But if you haven't, try to think for a moment which one of these two. I'm telling you that actually the question is which one of these two pictures is fake, generated by a computer. Yes, thank you, Mr. Professor Renaud, who has a chair on artificial intelligence. The answer of Jérôme is of course correct, but it is something which I do find impressive. And if I didn't give you this in the context of, a question like that, but if you saw these two pictures on the news or on some account or on some social media, etc., I claim that it is actually pretty hard to tell whether these persons are real or not. And we all live in an era where fake news is a very important and difficult and thorny issue. So you can imagine that with the proliferation of very easy to generate fake images like that, that's the website, this person does not exist, .com, you can see that this can be tricky. And if you want to play around with this type of AI-generated images and stuff, well, there's actually another companion website, which is a very good test of your abilities and of Jérôme's ability, which is this real or not? So you have to do a series of tests and decide, which one is fake. And that's a very nice thing to test out. But why I'm mentioning it and what does it have to do with learning in games? Well, how are these things generated? They are generated by something which is known as a GAN, a generative adversarial network. And if you think that this is cutting edge technology, this is not. This is something which has been around from 2015, 2017 or so, when it really became powerful. And if you think that 6 years is nothing, 6 years in ML and AI is prehistory. Okay, so this is definitely not state of the art. This is by now kindergarten. But how does this architecture work? It is very easy. You start with garbage. You start with some random number, all right? A vector of random numbers. And what you do is you feed them in a very powerful black box, which is known as a neural network. Now, Rida told me that some of you are coming from a data science background, so I guess that you'll know this. If you don't know what a neural network is, doesn't matter. Think of it as a black box, a very powerful computational device. And what does this do? Well, it tries to transform this random number that comes in and output something. Usually, it's going to be crap. All right. But then, what it does, and that is the genius of the architecture, is that it takes these crappy pictures and it feeds it into another neural network. And that neural network is has seen a lot of faces of real people, and then tries to decide whether this picture that the first neural network generated is fake or not. All right. And it outputs a probability of, this is true or not. And then, based on this output, the first network tries to learn, says, okay, so what I did, my configuration was not particularly good, so I am going to change things a bit and try to become better in order to fool the discriminating network. All right. And so this is an exchange which is happening very fast, much faster than you and I could ever hope to learn. And then what you're trying to do in this case is the first neural network is actually trying to the discriminator neural network is actually trying to maximize the probability of being able to tell fake from fakes and reals from reals. And the first generator is trying to minimize the efficiency of the discriminator's efforts. All right. So what is this? This is a game. This is training such a system, achieving a system which actually works well in practice is exactly like playing a minimax game. The problem is that this minimax game is not like the typical minimax games where like rock, paper, scissors, where we have 3 actions and stuff like that. This, you have to, you're trying to find solutions at a very, very complicated space. So you're literally traversing this sort of landscape, and you're trying to find somewhere there the lowest point in this valley. And the thing is that as you're trying to traverse this valley with a learning algorithm, this is where learning comes in, this is where optimization comes in, gradient descent algorithms come in, their variants come in. The thing is that as you're trying to do, the other network is also learning, and the thing is that every action, whatever the other network does, is actually creating an earthquake on your landscape, and it changes your landscape. And so what you end up having is you're trying to already have to solve a very difficult problem, finding somewhere a minimum hidden there, whereas the landscape changes all the time. All right, this is learning in games. This is rather what learning in games is in the world of artificial intelligence. Does it work always? No, it doesn't. I mean, you could take this architecture, again, train it for 8 days on very powerful computers, and still get crappy outcomes like that. All right, so definitely it doesn't always work. But what we are trying to do, at least in the part of this research field, which interacts a lot with AI and ML, artificial intelligence and machine learning, is to see when it does work. So for instance, there are, to try to understand certain, at least classes of games, where, okay, maybe at first you have a bad algorithm, so instead of converging, you're diverging. All right, so this is a case where the game is viable, but you don't have a bad algorithm, so maybe if you design a good algorithm, you will turn this divergence issues, this non-learning aspect, into something which is actually learnable and things work. And then, you know, sometimes you basically give up, because even there are just cases, there are just games that are very, very hard. But is this the end of the road? No, you're still trying to understand exactly what types of behavior you're getting in this case, what type of outcomes you get in this architecture and all that. So again, that is what learning in games, at least in this context, is. And more generally, you know, as a scientific field, I would have to say that it is at a very exciting interface of several fields. On the one hand, you have game theory, obviously. So you're trying to work with computation of equilibria. You're trying to understand what other solution concepts might arise in this very complicated world. On the other hand, you have you have a lot of interface with optimization and all the algorithms that are designed there, because you want to take the state-of-the-art algorithms and see how they operate, how they work in this multi-agent setting. And of course, you also have a very a lot of interactions with learning theory and online learning in particular, et cetera, which is a field which has to do with multi-arm bandits, adaptation, regret minimization, and all these nice things. So this is a very rich field with a lot of interactions with other scientific fields, and also with a very diverse range of applications. Already, some of them had been mentioned in the more econ or market world, but already, I mean, if we're talking about the fourth industrial revolution that we are currently undergoing, these are exactly the technologies that would end up powering stuff like autonomous vehicles, because that is, again, a learning system interacting with another learning system, you know, one car, another car, driving each other, so that's multi-agent learning for you. Or in other impressive applications like multi-agent reinforcement learning, if you are familiar with computers beating Go or StarCraft or all these things which were deemed impossible, they are powered again by the same thing, by the same type of algorithm. So, yeah, is this okay? So, all in all, why do A PhD in learning, in games, yeah. For me, this is a big part of the reason. But you know, if you ask me why I do it, why I do what I do, well, yeah, all of the above, sure. But as Edith mentioned, for me, another reason is, well, you know, I like math, I like computers. They are a very nice binary world where things either work or don't. You don't have any doubts like that. And most of all, I also like pretty pictures. You get to generate a lot of them. So yeah, it's fun. So you know, this is a big aspect of at least what I find exciting in this, and I hope you also do. All right, thank you.